Good morning, everyone. Welcome to today's webinar, Coding Laydown Variations, Discussion of Possible Causes and Solutions. This is Tim from AMCAL. Please feel free to ask questions in your question box in your control panel at any time during the presentation. Your questions will be addressed at the end of the presentation. Today's webinar is presented by Bob Pasquale. Bob is one of the founders and co-owners of New Era Converting Machinery, where he has served as president since 1996. Upon graduating from Stevens Institute of Technology in 1985 with a degree in mechanical engineering and metallurgy, Bob accepted a position as project engineer at Liberty Machine Company, a web converting machinery manufacturer that was founded by his family in 1946, and where he worked part-time prior to graduating. During his career, Bob worked in many areas of the business, including technical sales, project management, project engineering, manufacturing, engineering director, and new product development. He has 5 patents related to web processing. Bob has been active in several trade associations, including AMCAL, where he serves on the board of directors and regularly delivers technical presentations, just like today. He currently serves as the chairperson of the ICE USA Steering Committee. I will now turn the presentation over to Bob.
Good morning, everyone. I'd like to thank you for attending today's presentation. Couple of quick things. As Tim mentioned, any questions, feel free to type them and send them off to him, and we'll try to address them at the end of the presentation. Also, this presentation is really set up for a face-to-face type situation. So I will try to go a little slower than normal with some of the slides to allow for any lag that the internet may cause. Of course, the other advantage is doing it in this format, I won't be able to tell if I've bored anybody and put you to sleep. So today we'll discuss variations in coding systems laydown rates. As part of this, we'll review the possible causes for these variations and what actions can be taken to address them. So the goal of every coding operation is to maintain a consistent laydown rate throughout a run, as well as when applying the same coding at a future date. In order to provide this consistency, one must address those issues which can change a coding laydown or application rate over time. Now, these issues can appear either as a gradual drifting of the rate or as a sudden variation, and can result in either an increase or decrease in the applied coding amount. A wide variety of issues can cause these changes to occur. Many are specific to certain types of codings and coders, and some are what we'll call short-term, meaning they result in changes in the coding laid down within a single run, and some of them are long-term, occurring over extended usage or between product changes. So for purposes of this presentation, we'll divide these issues into the following 5 categories. Variations caused by changes in the coding, variations caused by solution handling equipment, variations caused by changes in the equipment, and by equipment we mean by the coder itself, variations caused by temperature changes, and lastly, variations caused by equipment usage and wear. And I point out that some of the topics or examples we'll talk about today may fit into more than one of these categories, but for the purposes of this presentation, we put it into a particular category. So for each category, we'll provide examples of how the coding laydown rate can be affected. And in certain cases, we'll take a deeper, more detailed dive into the example, and we'll discuss things such as specifics about what type of coding or coder it applies to, how it can affect the coding consistency, and what corrective actions can be taken. So let's start with variations caused by changes in the coding. So there's several changes that can occur in the properties of the coding that have an impact on the laydown rate. And these changes typically show themselves over the course of a run. So as we had mentioned earlier, they typically tend to be short-term issues. They can occur in either water or solvent-based coatings. And they can be found in a wide variety of coaters. So let's talk about a few examples of these issues. Let's start with changes in the percent solids. So this issue can occur in any type of coater where the coating is exposed for a period of time. A typical example of this is a pan-fed offset gravure coater like you see here when using a solvent-based coating. So as the coating sits in the pan, the amount of solvent, I should say, many of which evaporate under room conditions, continuously reduces. And this results in a continuous increase in the percent solids, which results in a continuous increase in the final coating laydown rate. So the chart on the right is an example of a 20% solid coating, and it illustrates the impact on the increase in solids as the solvent evaporates. So as you see from, I'll call it the magenta line, that shows the change in percent solids as it goes from 20 to 100%. And you'll notice that the change in percent of solids grows rapidly. Now, what can we do to address this issue? Well, a couple of things. First of all, the easiest way is to reduce the amount of coating that's held in the pan or pond, giving it less time to be exposed and therefore less time for solvent evaporation. Cover the pan or pond to reduce the evaporation or flashing. Or monitor the percent solvents and automatically adjust to correct for it. And there's systems that you can use that automatically does this, samples the solvent, and then continuously replenishes it. So next, let's talk about foaming of the coating. So an example of this is when using a pan-fed gravure coater where the coating has a tendency to foam. So as the coating sits in the pan, the turning roll causes this foam to form. And as this foam forms, it gets into the gravure roll cells, which results in a decrease in the amount of coating which is applied to the web. And over time, as the amount of foam continues to increase, more foam gets into the cell, less coating therefore gets into the cells, and the coating laydown continues to decrease. Next, let's talk about coating settling and separation. So this issue occurs when the solids in the coating begin to settle or separate from the solution that's holding them. And as an example, let's look at a nip-fed reverse roll coater. So as the coating sits behind the rolls, the solids begin to fall out of solution, settling toward the bottom of the puddled coating. So in this sketch, you see at the beginning a fairly even or uniform distribution of the solids. And in time, the solids begin to migrate toward the bottom of the puddle or pond. So as the percent solids of the coating closer to the metering to applicator roll nip increases, so too does the amount of solvent that actually passes through the nip and gets delivered to the web. So how do we address this issue? Well, again, as much like we talked about earlier, you can reduce the amount of coating in the puddle, which reduces the time that the coating has to separate. Or you can provide mixing hardware in the puddle, which continuously keeps the solids in solution or in suspension. So now let's move on to variations caused by solution handling equipment. So a major part of many coaters is the equipment used to supply the coating to the coater. And these solution handling systems typically consist of several components which can affect the coating laydown rate. So let's talk about a few examples of this. Let's start with coating aeration. So it's often the case that the circulation pump being used can result in air being mixed into the coating. And this can result in the air being delivered to the web as part of the coating, which would obviously cause a decrease in the laydown rate. Another issue is uneven or varying distribution of the coating. So for coaters where a pond or puddle of coating is used to supply the coater, an uneven or varying distribution of the coating to that pond or puddle can result in a variation in the coating laydown rate. And this issue typically occurs in coaters such as knife coaters like you see here on the right, reverse roll coaters, and between the roll coaters. Now this issue really shows itself when you get into higher viscosity coatings where the coating itself doesn't have a tendency maybe to flow out and give a uniform distribution within the pond or puddle. So how do we address this issue? Well, you can use a traversing delivery system like you see here that moves back and forth over the top of the puddle or pond and evenly distributes the coating into it. You can use a coating distribution manifold. So maybe instead of feeding the coating to the pond or puddle from a single point, you use multiple points or even a continuous manifold to feed the coating. Another feature that you could incorporate is using automatic pond or puddle level controls to prevent the puddle or pond from surging up and down, which could cause a variation in the coating distribution or the coating laydown. So next, let's talk about variations in pump speed. So there's several coating systems where the laydown rate is directly affected by variations in the solution handling system's pump speed. An example of this is a dye coater like you see here on the right, where the amount of coating applied is directly related to the amount of coating delivered by the feed pump. So there's several factors that can cause changes in the pump speed, including changes in the load on the pump due to factors such as changes in your coating viscosity, or drift in the pump motor's speed control. So how do we address these issues? Well, we can use a flow meter or to monitor or control the pump's output. Or as you see here, we can use a coating measurement system, a thickness gauge that will measure the coating laydown and automatically adjust the pump speed to compensate for these variations. Another issue is filter plugging. So for certain coating applications, variations in the coating laydown can be a result of these delivery systems' filters becoming plugged. And this can cause a drop in the flow rate to the coater, which will obviously result in a drop in the laydown rate. So how do we address this issue? Well, we can put a flow meter on the exit side of the filter to monitor the delivery rate and even use that to control the pump again. Or we can use differential pressure switches across the filter, where these switches tend to sense the increase in pressure that's associated with the plugging of the filter and therefore notify you that there is indeed an issue with the filter plugging. So next, let's move on to variations caused by changes in the equipment. And by equipment, we mean by the coater itself. So it's often the case that issues with the coating equipment can result in variations in the coating application rate. And these issues can arise from a wide variety of mechanical and electrical items, can affect virtually every type of coater, and can affect every form of coating. Now, of particular concern are those items used to adjust and set the coater's operating parameters, where any unwanted variations in these devices during operation typically result in an unwanted change in the laydown rate. So let's talk about a few examples. Let's start with changes due to variation in force. So certain types of coaters can be affected by forces that are generated by the coating being applied. An example of this is a between the roll coater, like you see here, where the coating can impart a separating force as it passes between the rolls. So any changes in the coating or the coater's operation over the course of the run can result in a change in these forces, and this change in force will lead to a change in the deflection of the rolls, which will result in a change in the laydown rate. So how does one address this issue? Well, first of all, assure that the coating being supplied remains consistent. Assure that the coater's operating parameters remain consistent throughout the run. And lastly, you can get very complicated, and as shown here, you can use deflection compensation via roll bending that's integrated with an automatic measuring system and therefore automatically adjusts for any deflection or any changes in the roll deflection. Another issue is drift and gap setting hardware. So many coaters rely on adjustable devices to change the gap between rolls, or the roll in a die, or a roll in a blade to allow for changes in the coating laydown rate. And the setting or position of these devices can be inadvertently changed during a run by several things, including vibrations, debris, operator's unintentional contact, or changes in temperature. And these occurrences can result in a change in the final coating laydown rate. Another issue is changes in gap setting as you jump a seam or a splice. So often the gap between two rolls, or a roll in a die or a roll in a knife, is cycled open and closed to allow for a seam or a splice to pass. And this cycling is typically done one of two ways, either by retracting the roll or die or blade, or by moving the gap setting device, by opening the gap setting device and then closing it again after the seam or splice passes. So what really becomes important is that the design assures that the gap is reestablished precisely after the cycling is completed. If it's not reestablished correctly, obviously you're going to have a change in your gap and therefore a change potentially in the coating laydown rate. Another issue is changes due to variation in roll speed. So several coating systems rely on the speed of a roll or rolls to deliver the proper amount of coating to the web, including multi-roll film split coaters like shown, reverse roll coaters, offset gravure coaters, kiss coaters. Now there's several factors that can cause variations in the speed of the roll, including, and this is very similar to what we had talked about for pumps, a change in the load on the roll in this case, due to factors again such as changes in viscosity or maybe changes in gap setting, or a drift in the roll's motor speed control. And in these cases, a change in the roll speed will change the coating laydown rate. So now let's move on to variations caused by temperature changes. So there's many ways that changes in temperature can result in changes in the coating laydown rate. And this affects a wide variety of coaters and can impact the laydown rate of solvent-based coatings, water-based coatings, and 100% solid coatings. And of particular note, we should think about the 100% solid coatings and think about hot melt coatings where temperature is part of the equation of delivering those hot melts, and therefore any changes in the temperature can change the coating laydown rate. So what are a few examples of this? Well, let's start with changes in gap as the temperature changes. And as an example of this, let's consider a nip-fed reverse roll coater, and let's assume we're operating in the winter. So at the start of the day, The room and the equipment may be at a low temperature. And as the day goes on and as you continue your operation, the temperature may increase from several factors, including heat being given off by the drying equipment or friction as the rolls operate. So let's look at a typical example of this. Now let's assume at the start of the day, it's 60 degrees in your room, and over the course of your operation, that temperature increases to 75 degrees. Well, we can actually calculate the change in gap between the metering and applicator rolls and look at that, how that affects things. So I'm going to throw a little math in. So we have a beginning temperature, as we talked about, of 60 degrees F. So this will be our TI or T initial. A final temperature TF of 75 degrees Fahrenheit. Let's assume an initial roll diameter of 10 inches. And we know that, we're assuming they're steel rolls. We know that there's the thermal expansion coefficient, which is the number you see here. So if we take those numbers and plug it into the bottom formula, which is the change in length equals the initial length times the coefficient of expansion times the change in temperature, you come out with a 0.001 inch or 1 mil change in the diameter of the rolls. So let's look at how that affects things. Let's assume at the start of the day, we set our gap at 5 mils, which is very typical for a reverse roll coater. So as the temperature changes, the roll's diameters change by 1 mil, as we said, where the radius changes by a half mil. So the two rolls' radiuses grow toward each other by a half mil each, resulting in the gap changing from 5 mils to 4 mils. So this 15-degree change in temperature equates to a 20% decrease in the gap from 5 mils to 4 mils, and therefore a 20% decrease in the amount of coating delivered to the applicator roll, and an associated change in the amount of coating being delivered to the web. So there's several ways to address this particular issue, including locating the coater in a temperature-controlled enclosure so that during the course of the run, the temperature of the coater stays consistent. Using rolls that are temperature-controlled, so it becomes very easy to keep those rolls at the same temperature regardless of the environmental conditions. Or using a closed-loop feedback device such as a thickness gauge, again, that automatically compensates for these changes to maintain a consistent laydown rate throughout the run. So another temperature-related issue is changes in the roll speed as the temperature changes. So as we've seen from the previous example, changes in temperature changes the size of the rolls. So for a system such as a KISS coater like shown, a speed-driven roll is used to transfer the coating to the web. And as the roll size changes, so does the roll surface speed. And this change in speed results in a change in the coating laydown rate. Another issue that arises from temperature changes is changes in the coating properties. And this is one of those where, we could have talked about this when we talked about changes in coating, but we decided to put it in changes regarding temperature. So let's talk about a solvent-based coating where an increase in temperature can result in an acceleration of solvent evaporation, which will result in an increase in the percent solids, which will lead to an increase in the final coating laydown rate. So now let's move to the last of our 5 areas, and let's talk about variations caused by equipment usage and wear. So there's several factors associated with the usage and wear of equipment that can result in a change in the coating laydown rate. These issues can affect every type of coater, can affect every type of coating, can be both short-term and long-term, and typically result in a gradual change in the coating laydown rate. So let's talk about a few examples of this. Let's start with coating buildup. So the buildup of coating on the coater parts during operation is a common issue that can affect many different types of coaters and can occur with many different coatings. And during the course of a run, it's typical that this buildup continuously increases and continuously changes the laydown rate. Now, fortunately, most issues related with coating buildup can be addressed through proper coating operation and good housekeeping. Now, a specific example of this is buildup of dried coating in the cells of a gravure roll over the course of a run. And this can be caused by several factors, including improper release of coating from the cells, poor doctoring of the roll, solvent flashing, and stops of the operation during which the coating dries in the roll. Now, all of these factors can be addressed through the proper setup and operation of the coater, including proper setup of the coating nip gap, footprint, and pressure to make sure that you get good release of the coating from the cells, assuring that the doctor blades are correctly set and maintained, maintaining the delivery of a consistent coating solution to the coater, and continuously re-wetting the roll on stops in operation so that the coating doesn't dry in the cells. Another issue that comes up is changes due to gravure cell pattern and doctor blade wear. So over the course of time, as a result of the forces that occur from roll doctoring, the cell pattern in the gravure roll wears, and the doctor blades wear. And this wear results in a gradual change in the coating laydown rate. So how do we address this? What can we do to mitigate the impact of this? Well, it's a couple of things. You can use ceramic gravure roll surfaces. Though they're more costly, because of their hardness, they obviously don't wear as fast. So therefore, you get a better and more consistent coating over a longer life. The other thing you can do is use a dynamic loading system on your blade that compensates for the wear in that blade so that you get a uniform and even and consistent wipe of the rolls. Next, let's talk about changes due to die lip wear. So a common occurrence is the wear of the lips in a die as you use it over time. And this wear will result in a gradual change in the coating laydown rate. So how do we address this issue? Well, one of the things you can do is regularly inspect and adjust the die lips, or even replace them as needed. Or again, you can use a closed loop coating measurement system that compensates for this wear, automatically adjusting, in this case, the pump speed to deliver the proper amount of coating. So the last thing I'm going to touch upon is changes due to rubber roll wear, swelling, and hardness. So there's a number of issues that can arise regarding the coater's rubber rolls that can impact the ability to provide a consistent, repeatable coating. These include wear due to usage, swelling of the rubber due to exposure to various chemicals, and that's not just during operation, but that's often also due to cleaning of the rolls, and changes in the hardness of the rubber. Now, these issues can have various effects on the coating laydown rate due to changes in the gap or interference between rolls, which can affect how the coding is transferred from roll to roll or roll to web. Changes in the footprint of the nip, which again can affect transfer from roll to roll, or in the case of gravure, the inability to properly remove the coating from the cells, or changes in the surface speed of the roll, which again can impact the transfer of coating and the proper laydown rate. So in conclusion, there's many factors that can affect the coder's ability to provide a consistent laydown rate. And what really becomes important is to evaluate the coder's operation to determine what factors may be affecting it, and then develop a plan to address those factors. So that ends what I'll call the formal presentation portion. So Tim, I'll turn it back over to you. And if there's any questions, we'll take a shot at addressing them.
Great. Thank you, Bob. Great presentation. I think you did a really good job presenting, because at this point, we don't have any current questions. I want to remind everybody, if you do have questions after this webinar, you can reach out to Bob. His information's on the screen, bob.pasquale@neweraconverting.com. Or if you have questions beyond this, feel free to contact me directly at tim@amcal.org. We would like to thank everyone for attending, and a special thanks to Bob Pasquale. Please be sure to check out www.amcal.org for upcoming webinars and all of our continuing education events. This webinar will be posted on our website within AmCal TV, available to all AmCal members. Thank you for attending. Please be safe out there and have a great day.